Lecture 30 of Physics 72 discusses magnetic energy and inductor capacitor circuits or LC circuits. These are found in 30.3 and 30.5 of University Physics. Please take time to read the objectives. You may pause the video if you like. From the previous lecture on inductance, the inductor was introduced as a circuit element that resisted changes in current. Usually seen as a solenoid, but it can take on different forms such as a toroid. Inductors induce EMFs in circuits and have potential drops across its nodes equal to LdI over dt. We're going to use this in understanding more about the inductor's role in a circuit. Comparisons with capacitors and inductors were also made in the last lecture. In vacuum, they both share geometry-only dependence as seen in the examples of a parallel plate capacitor and a solenoid. This property extends to all configurations as long as the system remains in vacuum, or free space. The potential drops across a capacitor and an inductor also share the same quality of being dependent on the charge of the circuit. While it isn't as obvious in the case of the inductor, remind yourself that current I is just the rate of change of Q over T. Quick algebra shows us that the potential drop across an inductor is dependent on the second derivative of charge with respect to time. So as you can see here in this part of the graph, or the table, I'm sorry. We invited the possibility that the inductor may be the magnetic counterpart of the capacitor previously, since derivations of capacitance dealt with electric fields, and derivations of inductance dealt with magnetic fields. And the first part of this lecture explores that possibility even further with storage of energy. We derived from several lessons ago that capacitors store electrical energy between its plates. Now, not much is known about the energy storage capabilities of inductors, but it may be good to guess that it has something to do with inductance and magnetic fields. This invites us to look at magnetic energy. For the first part of the lecture, we try to see how else inductors contribute to circuits. We also dive deeper into the similarities of capacitors as energy storage devices. Our lesson in circuits then had us conclude that power is involved whenever there is a voltage drop across any circuit element. For capacitors, it meant that the energy was being stored or distributed via electrical energy. For resistors, it meant that energy was being dissipated as heat. Since there is a voltage drop across an inductor whenever there is a change of current, we can explore how power plays into these elements. Now, power delivered from an EMF source, or our inductor, is given by P is equal to IV. Now, substituting our known expression for V, we have LdI over dt times I, as the power delivered from our inductor. Power then bridges us to energy, as we know that instantaneous power is just the time derivative of energy. Rearranging terms, we arrive at an element unit of energy in terms of an element unit of current. Now, with di as the integration variable, we integrate from an initial value of the current that we take to be 0 to some final constant value I, or equal to this. Now, we now have an expression for energy stored in an inductor as U equals 1/2 Li squared. Let's try to make sense of what we just got. The energy stored in the inductor as the current increases from 0 to a final value I is given by U equals 1/2 Li squared. The inductor can also act as an energy source once the current decreases from I to 0, as it tries to resist this decrease. The value of U in the storage and supply should be the same, which implies that the energy is conserved. This means that the energy that is stored in the inductor as current increases should be the same as the energy that the inductor supplies to the circuit once current starts to decrease. Now, at this point, we have to consider something that is usually overlooked. The I in the expression is just the final value. For inductors to be more than just mere wires, time-varying currents must be present. So that I that you see, that's highlighted in red, is not a constant value. Because the moment that you introduce the moment that your current in the whole circuit is just a constant value, your inductor just acts as a simple wire. So this total energy U, or the I that is in this total energy U, is already the final value or the maximum value that this current possesses. We haven't specified what type of energy is stored in the inductors yet. To shine some light to what that can possibly be, Let's go to a specific configuration for an inductor, a solenoid. You can get the same result with other shapes, but this may be the simplest one. Expressing L as the solenoid inductance from the last lecture, we get total energy as U equals 1 half mu naught N squared AI squared over L. Now, we can rearrange this expression in a way that the magnetic field of a solenoid, being mu naught times Ni, appears in U. U can then be re-expressed as 1 half mu naught B squared times L times A. Now, this B squared is already, after rearranging everything, it's the expression in orange. From its dependence to the magnetic field, we can then say that the energy stored in an inductor is magnetic. So we index U with a B to distinguish it from the electric potential energy that's seen in capacitors. As stated a while ago, we know that power plays in the resistor as dissipated heat. Like a lot of thermal processes, this is irreversible, or that means it can't just fan the energy back to the resistor. This isn't the case for the inductor, as energy stored from the inductor can be brought back to the circuit as the current decreases. Considering that inductors can come in different shapes and sizes to fit a specific inductance value, it may be worth considering a geometrically independent quantity in describing its capability to store energy. Like what we did with capacitors, we obtain an expression for energy density for magnetic energy. We divide our expression, big U sub B, by the volume of the shape the inductor possesses. Typically, a solenoid is shaped like a prism, so its volume should just be the cross-section multiplied to its length. Convenient that our expression for total energy already has the AA term, we can just cancel the terms out, giving us an expression for small u sub b equals 1 over 2 mu naught times b squared. Now, should the inductor be immersed in a magnetic material, all we need to do is simply replace mu naught with mu. But then again, that's out of the scope for Physics 72. The usefulness of this magnetic energy density term is that this expression is true for any configuration, and it's not just for solenoid inductors. Going back to the electric energy density of capacitors, we begin to see its striking resemblance to small u sub b. Our parallelism of inductors to capacitors now becomes more obvious. With our newfound knowledge of magnetic energy, we can now complete the comparison table for capacitors and inductors. The similarities of these circuit elements will play a role in the next section, the inductor-capacitor circuit. So let's try to answer a problem before moving on to the next topic. A solenoid of 25 centimeters length with a cross-sectional area of 0.5 cm squared contains 400 turns of wire and eventually carries a steady-state current of 80 amperes. We're calculating four things. 1. The magnetic field of the solenoid. 2. The energy density, small u sub b of the solenoid when it is filled with air or vacuum. C. The total energy, big U sub b, in the coil's magnetic field, which we assume to be uniform. And lastly, the inductance L of the solenoid. First, we identify the given variables before answering the questions. So L is equal to 25, N is 400, A is 0.5 cm squared, and I is equal to 80 amperes. Starting with the magnetic fields of the solenoid, it's a simple substitution that leads us to mu naught times N times I. And that should give us 0.161 Tesla. Energy density is also a direct substitution since we already have an expression of B from letter A. Our answer then, after substitution, should give us 10.3 kilojoules per meter cubed. We can then transition from energy density to total magnetic energy without having to use our original expression for big U sub B. Multiplying our answer from B with the volume of the solenoid, we get the total energy to be 0.129 joules. While it may seem like the energy pales in comparison to the energy density, note that inductors usually come in minuscule sizes to fit circuit boards. We can also solve for big U sub b using 1/2 Li squared, but this requires us to solve for the inductance first using a lengthy expression. But honestly, it's up to you how to solve the problem. To answer the last question, we find the value for inductance L by isolating it from the UB equation, And this gives us, eventually, after substitution, an inductance value of 4.06 times 10 raised to the negative 5 Henry. And again, to reiterate, you can solve inductance using the geometry-related terms exclusively. The method and order of solving this problem is entirely up to you. Going through another quick example, let's try to figure out how much current is needed to store an energy of 7.2 kilojoules in a coil with an inductance of 100 henries. It's pretty simple. Isolating I from our expression for big U sub B, and direct substitution gives us 12 amperes for current. It's pretty powerful. Moving on to the second part of the lecture, we begin to explore how inductors interact with other circuit elements discussed so far. We skip resistor inductor or RL circuits in the book since its dynamics is almost identical to RC circuits, and that's already discussed before. You may wish to read it in 30.4 as a supplementary material. An uncanny similarity of LC circuits to a physical system discussed way back in Physics 71 will be explored in detail in the coming slides. The LC circuit's name is rather direct to the point, a circuit containing an inductor and a capacitor. We know that a capacitor stores electrical energy from the amount of charge its plates contain, and an inductor stores magnetic energy via currents. Let's understand how charges and currents act in an LC circuit with the basic configuration, both of them connected in series, as you can see in this figure here. Now, as a starting point, let the capacitor C be fully charged with Q, with no current running through the whole system. Total energy would be exclusively in the capacitor and none for the inductor, because as I said a while ago, there's no current yet. Slowly, the capacitor discharges as the charges flow away from the left towards the other plate, which introduces a counterclockwise current. As the capacitor discharges, the electric energy decreases and gets converted to magnetic energy because the current increases in value. At some point, the net charge at the capacitor would be zero, completely discharging it, and all of the energy in the system would now be magnetic, because current would be at its maximum value. After this tipping point, the positive charges accumulate on the right side, and the current changes start to slow down. This means that the energy gets converted from magnetic back to electric. The capacitor eventually gets recharged back to Q, but then the polarities will be reversed. The positive charges would now be on the right. It's also at this point that energy is completely electric again, as the current stops flowing. Finally, the positive charges start going back to the left plate, and a reversed clockwise current begins to ramp up. Step 4 is like step 2, with zero charge, but then with maximum current, with the main difference being the direction of the current is now clockwise. Past this point, the system eventually returns to step number 1, with plus Q back on the left plate. And with this, our LC circuit cycle is complete. The movement of charges and current values oscillate between minimum and maximum values, which we'll get to in a bit later. Before moving on to the next slide, I'd like for you to turn your attention on the energy graphs on the left. Notice that while the magnetic and electric energies are always changing, their total energy E remains constant. This phenomenon is similar to energy diagrams you've seen before in Physics 71, with the relevant energies being kinetic energy and some conservative potential energy. We start to see one similarity of the LC circuit with a mechanical system. This slide provides a larger picture of the LC circuit cycle. What's not as obvious from the previous slide is that values of charge Q and current I oscillate between phases. At max Q, the current, or the change of Q, is 0. At max current, the total charge is 0. This interplay between variables is also something that's been encountered in mechanical systems in Physics 71. So to drive the point that an LC circuit shares likeness to mechanical systems, let's look at it quantitatively via Kirchhoff's rule. Let the capacitor have some initial charge plus Q equals CV on the left plate. Assume that current is running clockwise, and let's set the loop path to be clockwise too. From Kirchhoff's loop rule and conventions that we set from previous lectures, it would give us Vc being equal to negative Q over C, and VL being equal to negative L di over dt. Now, we substitute it to the equations of Kirchhoff's rule, and then we have this. Our goal is to obtain a differential equation that looks like something we've seen before in Physics 71. Noting that current is just equal to the time derivative of charge, our equation becomes dependent on one variable. Our final equation then becomes L d squared q over dt squared plus qc equals 0. The form of this equation bears a close resemblance to md squared x over dt squared plus kx equals 0. This is the differential equation for simple harmonic motion of a spring mass system. Another piece to the puzzle that LC circuits act like a familiar mechanical system. Upon reviewing the similarities we've stated in the last 3 slides, namely the energy diagram similarities, the oscillating values for charge and currents, and the differential equation, we can confidently assert that this LC circuit has a mechanical counterpart, the spring mass system. Now would be a good time for a throwback to your Hooke's Law dynamics in Physics 71. Recall the system. A block of mass m slides on a frictionless plane as it's attached to a spring of constant k. The working equations are F equals ma equals negative kx. Describing acceleration a as the second derivative of position with respect to time, and a bit of algebra, we get d squared x over dt squared plus k over mx equals 0. For convenience, we express k over m as omega, a nifty substitution that we'll see later. The solution to this differential equation leads to periodic functions, with x equals a cosine omega t plus phi, and v equal to negative omega a sine omega t plus phi. We use cosine to follow the initial condition that the spring is fully stretched from equilibrium to its amplitude a at the start. Now, omega a is our expression for the maximum velocity of the system, and that occurs at the middle when the spring is unstretched. The added term phi is there just in case we start at some point that is not at its amplitude. But normally we just set it to 0 for simplicity, and it is 0 in this case because we start at the amplitude. Omega is actually the angular frequency, which makes it convenient, and is just equal to square root of k over m. Now that we've reviewed the spring mass system, let's see how it compares to the LC circuit. We begin with similar looking differential equations, but with different expressions for the angular frequency. Looking at the differential equation of the LC circuit, we can set omega to be equal to square root of 1 over LC. Instead of position x, our variable now is charge q, or the charge at the capacitor, with the solution of qt is equal to capital Q cosine omega t plus phi. Now, capital Q here is the maximum charge. Current is just the rate of change of charge, and a single differentiation gives us its solution, being it is equal to negative omega q sine omega t plus phi. From here we can see that omega q is just the maximum current that our circuit achieves. Phi is the added term just in case we start at some point where the capacitor is not fully charged. Looking between systems, we see that instead of position x as our main variable, we have q for the LC circuit. Instead of velocity, we have current. As mass m is the resistance to motion or changes in velocity, inductance L is the resistance to changes in current. Finally, spring constant K is the amount of force needed to move an object a single unit of distance. Its counterpart is the reciprocal of capacitance, or the potential needed to add a unit charge to a capacitor. From the comparisons, one can see that the spring mass system is a robust analog for the LC circuit. It makes analyzing something as abstract as circuits a lot easier because for a spring mass system, we can actually see it. Diving deeper to frequencies, the oscillation frequency f is just obtained in a familiar manner, with our LC circuit expression being equal to f equals 1 over 2 pi square root of LC. Period, like when we discussed periodic motion, is just the reciprocal of f. But in the context of LC circuits, It's the time it takes for the LC circuit cycle to complete, well, one revolution. Going to applications, let's say you want to slow down this oscillation frequency. If you look at the equation for F, you can do this by just choosing capacitors or inductors with high values. Now that makes sense, since larger values for L and C means it takes longer for the capacitor or the inductor to store energy, or release energy for that matter. Like what we did in spring mass system, let's try to analyze the graphs of the functions of capacitor charge Q and the current in the circuit I. First, let's take note of the maximum values of both graphs. The maximum value of charge is capital Q, as expected. You can see in the dotted lines. From this, we can also get the maximum value of I as omega Q, which is not as obvious. From our discussion of the LC cycle a few slides back, you may have observed that the capacitor is fully discharged whenever current reaches its maximum value. Conversely, current stops flowing when the capacitor is fully charged. We can also observe this interplay between dynamical variables in spring mass systems. The block moves fastest when the spring is completely unstretched, and it stops moving when the spring is maximally stretched. This relationship is elegantly described by sine and cosine functions, with one being 0 while the other one is at maximum value, or maximum amplitude. Finally, you can also see that since we started with the capacitor fully charged, our phi should be able to be set to 0. And if phi is set to 0, cosine 0 is basically your maximum value. With these graphs, we finally completed our second objective in obtaining functions for Q and I of LC circuits. So now we go to an example to deepen our understanding of charges and currents in the LC circuit. Please take time to read the problem. You may pause if you wish. Please take note of the given variables. We're asked to get A, the maximum charge of the capacitor, as well as B, the oscillation frequency F. Finally, using the function I, t, we're asked to find the energy stored in the inductor at a specific time, that being this one, 2.5 milliseconds of oscillation. Now, before we go through the solution, please make sure that your calculators are set to radians, as this is the SI unit for angle values. To answer A, we recognize that we can get maximum charge Q from I sub max equals omega Q. Q is just then equal to I max over omega. And with proper substitutions, we determine the maximum charge to be 7.5 microcoulombs. Oscillation frequency is just a simple substitution of values, which then we should get 1.59 times 10 raised to the 4th hertz. Finally, the energy stored in the lone conductor is just the total magnetic energy. The inductance is already given to us. So all we need to do is substitute t equals 2.5 milliseconds for our function for I sub t, or I t. This should give us an answer of 2.12 times 10 raised to the negative 2 joules. Finally, to accomplish our last objective, we look into energy conservation in an LC circuit. From this discussion, we can see the interplay between capacitor charge and circuit current. Recall that the total energy in a spring mass system is just the sum of its kinetic and elastic potential energy, or 1/2 mv squared plus 1/2 kx squared. We can assume that this total energy should be constant in the absence of dissipative forces like friction. As we've already seen in some diagrams at the start, the total energy of an LC circuit is just the sum of its magnetic energy, which is stored in the inductor, and electric energy, which is stored in the capacitor. This should be equal to 1/2 Li squared plus 1/2 k squared over c. Notice how it resembles the total energy of the spring mass system. How do we know that energy is conserved in this LC circuit? Well, as the circuit counterpart of the spring mass system, we know that the energy will be conserved if the dissipative circuit elements are absent. This means no resistance in the circuit, or no resistors in the circuit, because that will be for the next lesson for our LC circuits. If the total energy of an LC circuit is constant, we can equate its total energy at an initial configuration to some final state. So that equation should be 1 half Li naught squared plus 1 half Q naught squared over C is equal to 1 half Li sub F squared plus 1 half Q sub F squared over C. So on the left side would be your initial values for current and charge. On the left side would be your final values for current and charge. To end the lesson, let's go through a quick example. An LC circuit with an angular frequency omega starts off with 0 current and charge capital Q. What is the current when the charge is capital Q over square root of 2? Now, to answer this problem, our fairly obvious hint suggests using the conservation equation, which is stated here. In answering the question, we first recognize that the starting current is 0, the starting charge is at maximum capital Q. The final charge is at capital Q over square root of 2, and we're looking for the final current. We substitute all of these values to the conservation equation, and like in Physics 71, isolate I sub f. With a bit of algebra, and recognizing that omega is equal to 1 over square root of LC, we get the final answer to be I sub f equals omega q over square root of 2. So that's it for this lecture, and thank you very much for listening.